Alright, so what we're going to do today is numerically integrate simultaneous differential rate equations. Okay, so things you need to be able to do by the time we're done today is to set up and numerically solve differential equations given a mechanism and the rate constants. You need to be able to investigate after this. Okay, so today we're going to do a demo on how to do this in Mathcad, and then in that handout I gave you in the exploration section, you'll be investigating reversible and irreversible parallel first order reactions, and you're going to learn about kinetic and thermodynamic control, and you're going to investigate the validity of the pre-equilibrium and the steady state approximation. Okay, but we're just going to focus for now on just how to do it in Mathcad, and then you'll be exploring these different mechanisms later. Okay, so for multi-step reactions, the integration of the rate laws and finding a closed form solution to the integrals is frequently impossible. What do we mean by a closed form solution? A simple function, like for example, if you have your rate equation is, let's say, dA dt is equal to k times a. What's a closed form solution for this? You integrate this and you get a equals a naught e to the negative kt, right? Where a is the concentration of a reactant. Okay, so that's an example of a closed form solution, and so you get a as a function of time, right? Now, frequently, especially if you have multi-step reactions, you cannot just get a simple expression like this that says a is this function of time, species B is this function of time, species C is this function of time. So we need to be able to know how these concentrations depend on time, and pretty much the only choice we have in these cases is to go by the numerical route. Okay, so we solve these differential equations numerically, and Mathcad is a very convenient tool for doing that. It has several built-in functions for solving differential equations. They're based on what's known as the Runge-Kutta method. And so for this particular activity, we're going to explore the reversible reaction, A going to B and B going back to A. Okay, so the rate constant for the forward reaction is K1. We're going to say that that's 10 to the 6 per second. And so this is what the system we're going to study. K2 would be K negative 1, the reverse. The rate constant for the reverse reaction would be 10 to the 6 per second also. Okay, so I'm going to show to you how you can numerically integrate this the rate equations for this. Now, you've seen this before. There's a closed form analytical solution for this. Yes.
K negative 1 equals 10 to the 6. Is that an S? Negative 1?
10 to the 6 per second. Yeah. Reciprocal second. So, what was I saying? Sorry. So we're going to demonstrate how this is done. Oh, I was saying that there's actually a closed form solution to this, and you've seen this earlier in the earlier lectures, right? And you can go back to that MIT lecture. He gave you the closed form solution for this. So now Mathcad doesn't like subscripts that have a negative in them. So instead of k sub negative 1, we're gonna call it K1R to call it K1 reverse. Okay. So instead of calling this K negative 1, we're gonna call it K1R. And for the forward reaction, instead of calling it K1 to make a distinction, we're just gonna call it K1F. Okay. So K1F and K1R would be the rate constants for step 1. If you had a multi-step reaction, then the rate constant for step 2 would be K2F for the forward and K2R for the reverse. Instead of K2 and K negative 2, we're going to use we're going to add F, okay, and R to our labels. All right, so this is what we're going to look at. We're going to look at this simple system right here. So how are we going to do this on Mathcad? First thing you need to do is set your Mathcad's 0 tolerance to 300. You want to make sure that By default, Mathcad sets anything that comes up to be 10 to the negative 15 or less to 0 automatically. So we want to make sure Mathcad doesn't do that while we're doing our calculation. So how do you do that? You go to Format, Result, Tolerance. Okay, by threshold, the 0 threshold is typically 15. That means anything less than 10 to the negative 15 is automatically set to 0. Let's just make sure Mathcad doesn't do that. So let's set that to 10 to the negative 300. So set your 0 threshold to 300. Okay? So we've done that. And then the next thing we need to do is define a concentration vector. Okay? And this would be a matrix in Mathcad. It's just a one-column matrix. And what you'll put in your concentration vector would be the initial concentrations of whatever species is involved in the reaction. So So if you have species A, B, and C, you're going to need a 3-element vector. Okay? So it's a one column by 3 rows. But since we're just doing A to B, how many elements do we need? We just need 2, right? So what I'm going to do is right here. I'm going to define a vector. Oops. I'm going to call it vector x. So I'm going to say x colon, and when you type colon, that will show you x colon equal. And how do I define a vector? I go to my menu, my toolbars over here. Here's a vector and matrix toolbar. Okay, and then insert a matrix there. And what do I need? How many rows? 2 rows, and just a one column matrix. So this is a vector. Okay, so we're going to assume that our reaction A goes to B and B goes to A. We're going to start with 1 molar. Let's say a concentration of 1 for A and 0 for B as our initial concentrations. Okay, we'll make things simple. At the beginning, we have 1 mole per liter of A and 0 for B. We're not going to put units to make things simple. So we'll just assume the concentration of A is 1 at the beginning. Okay, and the concentration of B is 0. Okay, so in this, you'd have this first element. This is called x sub 0. That's the concentration of A, initial concentration of A. And this is x sub 1. That's the initial concentration of B. You got that? Okay. Mathcad starts counting from 0. Okay, so 0, 1. The first element in your matrix, in your vector, is x sub 0. The second element is x sub 1. You can verify that. Okay, if you type x, open bracket, you have to type x, open bracket, and then 0, for example, if you want to know what x sub 0 is. Okay, x, open bracket, 0, and you type equals, you can see it spits it back out to you. X sub 0 is 1, right? If you want to know what x1 is, want to verify that it got the right value, so x open bracket 1, okay, equals, and you can see x1 is 0. Okay, if I were to change this to, let's say, 3, what will happen? You can see x sub 0 is 3. Okay, so I'm just going to change that back to 1. Now, make a distinction between this and x dot 0. Okay, if you type x dot 0, x dot 0, okay, x sub 0, I ask Mathcad for it, and Mathcad will tell me I don't know what it is. So it gives me a colon equal, because when you say x dot 0, that 0 is not treated as a number. It's part of the name of the variable. So when you use dot to make a subscript, a dot will give you what's called a literal subscript. Okay, that will be part of the name of the variable. If you use open bracket, that means that the thing that follows has to be a number. It's what's called an index subscript. Okay, so this 0 right here, huh?
How do you get the level 0 dot?
If you want a particular element of a matrix, you use open bracket. That will give you the index subscript. If you just want subscript that's just part of the name of the variable that is like t initial, t dot initial. So you would say t dot initial. Okay, if that's just a name, part of the name of the variable, then that would be what you would call a literal subscript. Okay, so use an open bracket to get an index subscript. Okay, so let me just get rid of this. Okay, and this one, I don't need that. Okay, so we've defined our initial concentrations. What do we do next? So you have your concentration vector. Okay, if we call this vector X, matrix X, then it's going to store the concentration of A in element 0, the concentration of B in element 1. Okay, and so we're going to initialize our vector X with the starting concentrations, and that's what we did here. Okay, so what I did here was I put down the initial concentration of A and the initial concentration of B. All right. Now, after that, you need to define your derivative vector. Okay? The derivative vector is where you will store the rates of changes. That means the dA dt, the dB dt, and so on. So if A is your first element, okay, then dA dt is going to be the first element of your derivative matrix. Okay, so you have a derivative matrix. Let's call that D. Okay, we're going to define our derivative matrix D as a function of time and X. Okay, and X here is the concentration matrix. So your derivatives, remember, are functions of time and concentrations, right? So you need to define your derivative matrix as D, and then the first thing you enter there is the derivative with respect to what variable? The variable we're differentiating against is time. And so derivative of X with respect to time. Okay, so we're going to define that. Oops. Colon. And then what kind of matrix do I need? How many species do I have? I've got A and B, 2 species, so I need a vector with how many elements? 2 elements. So 2 rows and 1 column again. Okay? And what I'm going to do here is write down the expression for dA dt, derivative of A with respect to time, and for this one, this would be the derivative of B with respect to time in here. Okay, what's the expression for dA dt? Let's look at our mechanism again. A going to be the rate so the rate, and then B goes back to A, right? So this is step 1F, this is step 1R. Okay, what happens to A? So you say dA dt is equal to 1. I'm just going to remove the brackets to make things simple, okay? So it's being lost in step 1, so minus V1F, right? In the forward step 1. Okay, you're losing it in the forward process for step 1, and you're making it in the reverse of step 1, right? So plus V1 reverse. Okay, negative V1 forward plus V1 reverse. So what's that equal to? Negative K1 forward. First of all, what are the rates for this? V1F is what? It's K1F times concentration of A, right? That's a unimolecular reaction. What is V1R? That's also a unimolecular reaction. It's K1R times B. So this is K1F negative K1F times A plus K1R times B. Okay? But what did we say A was? This is x sub 0, right? And b is x sub 1. So that's how we're going to define it. So over here, we're going to say this is equal to negative k dot 1f. Now, when I'm doing my subscripts here, this is k dot 1f. So 1f is part of the name of the variable. Okay, k dot 1f times x sub 0. So to enter this one right here, I need x open bracket 0. Okay, say x open bracket 0. 0, number 0, not the letter O. Okay, so negative k1f times x0, space bar to get out of the subscript, plus k dot 1r. Okay. So this is k dot 1r times what? B is x sub 1, right? So this is going to be x open bracket 1. So that's dA dt. The first element of your derivative matrix is the derivative of concentration of A with respect to time. You got that? You keeping up with me? All right, good. Now, what is dB dt? The second element here is going to be dB dt. Okay, so this is going to be dB dt. We need to enter dB dt there. So what's the expression for dB dt? Let's look at B. It is formed in step 1, right? So that's plus V1F. What happened to it in the reverse of step 1? You lose it from the reverse of step 1, so minus V1R. Okay? So that's your dB dt. And so that's equal to, what's V1 forward? K1 forward times A minus V1R is K1R times B. Okay? So if that's the case, then that's going to be K1F times X0, since A is X0, minus K1R times X1. So call it out for me. What should I enter here? Tell me what letters to press on the keyboard. Catherine? K dot 1F times, which is shift 8. X open bracket 0, that's X sub 0, and then space bar, and then minus K dot 1R times X open bracket 1. Okay. All right. Now Mathcad's complaining that it doesn't know what K1R is, what K1F is, and what. Okay. It doesn't know what K1R is. So we have to tell it before we actually define this. We have to tell it what K1F and K1R are. So K dot 1F equals, what did we say our K1 forward is going to be? 10 raised to the power 6. Okay, and K dot 1R is also 10 to the 6. Now it's happy. Okay, so let me just line these up to make it look neat. Align regions across. Oops. Okay. So you all caught up? So that's your derivative matrix. So you have a concentration vector and a derivative vector. Okay? And this derivative is derivative with respect to time. Okay? Of the concentrations which are stored in matrix in vector X. Okay, now that we've defined our derivative vector, we've defined our rate constant, what do we do next? You decide how long we want to integrate our rate equations. Okay, we're going to define this as T max. Now, a good starting point is to take a value close to 1 over K1 if the first step is unimolecular. If it's bimolecular, a good starting point, okay, would be 1 over K1 A naught. Now, you can always adjust this later because it's really just up to you how far you want the integrate, how far in time you want to follow the reaction. Okay, so these are just good numbers to use because 1 over K1, if you have a first order process, first order reaction, 1 over K1 will just be the lifetime. Okay, ln of 2 over K1 is the half-life. So that would give you a good enough range so you can see significant change in the concentration of your reactant. So let's just use 1 over K1. So let's define our T max then. Okay, get rid of these. Let's define our T max. Where was I? So I'm going to define my T max to be T max is 1 over K1, but I don't have K1 defined. What did I have defined? K1 forward, right? So K dot 1F. And let's just verify what that number is. It's 10 to the negative 6. Okay, so if your rate constant, first order decay constant is 10 to the 6 per second, you're going to use, we're going to follow the reaction up to about 1 microsecond. So 1 times 10 to the negative 6 is my T max. Okay? You still with me? Okay. Now, we decide how many intervals we want Mathcad to calculate because we want to calculate it at different times, right? From time 0 all the way to T max. So a good number, you don't want to use too few points because Mathcad solves these differential equations numerically, and if you use too few points, the gaps between time intervals would be too large. It might not converge, okay? So, and you don't want it to be too many because it's going to take forever to calculate. So a good time interval, maybe 100 data points from time 0 to T max. So that's a good number to use, and you can always change that later. You can extend it further, okay, if you want to follow it further in time. Okay, so I'm going to put endpoints. We'll define that as, we're going to call that endpoints. You can call it any variable name you want, but you need something descriptive, so endpoints is a good name for that variable. So we're going to define endpoints to be 100, okay? So we're going to look at 100 data points from time 0 to time T max, okay? Now, finally, okay, we just feed all of this information to one of Mathcad's differential equation solver. The one we're going to use is the rkAdapt. This is an adaptive Runge-Kutta procedure for solving differential equations. If you want to learn more about this, you're going to have to take a course in numerical analysis, numerical methods. But I will just take this, as far as this course is concerned, we'll just take this as a black box, okay? The output of the rkAdapt function is a matrix. So once so you can define a variable to be equal to a matrix that will hold the result, okay? And it's going to have endpoints plus 1 rows, okay? Because you're going to, from 0 to 100, let's say you have 100 points, right? It's going to start at time 0, and then you have 100 points after that. So that's going to give you 101 rows, okay? So what will happen is the first column of that matrix, the output matrix from that, will have the times at which, so this will be the time, the values of t at which the equations were evaluated, and then the other columns will have the concentration. So you'll have a column of time, a column of concentration of A, another column for concentration B of B, and so on, okay? So the way you would set it up is you simply define a variable as a matrix, variable equal to rkAdapt. And what are we doing here? We're specifying what is x here? That's the concentration matrix, right? It doesn't have to be x. If you didn't call it x, you put whatever you call it, right? You can call it conc if you wanted to. But since we define our concentration matrix, our concentration vector as x, we put x there. What is this 0 right here? That's the number. That's the number 0. That's the starting time. Okay. So x is the concentration vector. 0 is the starting time. T max is tells Mathcad how far we want it to calculate the result. So this is T max. Number of points. That's how many points we want, how many intervals we want from 0 to T max. And then what is this D right here? This is our derivative matrix, right? Our derivative vector. So you do rkAdapt, and then x, 0, T max, endpoints, and D. So let me go ahead and enter that. Type that in. Okay. So let's say I'm going to define matrix Z as my results. So I'm going to put my results in matrix Z. And matrix Z is calculated using the rkAdapt function. And what do I have to type here? 0 first. And by the way, Mathcad is case sensitive, so when you type rkAdapt, it's just the first letter that's capitalized, okay? So 0, and then after x, right? And then after x, what do I type? Starting time, 0, ending time, T max, comma, number of points, comma, and then the derivative vector D, close parenthesis. And now, Mathcad, if it doesn't complain, that means it was able to do the differential equation. Okay? What you can do is you can extract from Z, the time and the concentrations. Okay? So what I can do, for example, is I can define T of N. Okay? Let me zoom in on this one. I can now say T of N, time at point N is going to be, this would be the first column of matrix Z. So I want the column 0. Okay, remember Mathcad starts counting from 0. So I'm going to say column 0 of matrix Z. And if you look at this matrix toolbar right here, this M with the less than and greater than sign next to it, okay, this is where you specify the column that you want. So I want column 0. So if I put if I put a 0 there, then that's telling Mathcad I want column 0. Okay. So here what I'll do is I'll say I want the column 0 of matrix Z. Okay. And I want the nth element. So this one right here. The subscript there tells Mathcad that you want the nth element. Okay, so right there. I'm sorry, not that one. Let's see. Dot, no, open bracket. Okay, open bracket. Okay, and then n. This one tells Mathcad I want to assign column 0 of matrix Z, the nth element of column 0 of matrix Z to be the value of time, the nth point for point N, the value of time for point N. Okay? And let me see if I can plot. I'll show T here. T of N. So I'm gonna say T equals. It's not doing it. N equals 0, 1, all the way to n points. T of N equals. Okay, there it is. Okay. I have to specify what values of N I want. Okay. No, that should not be the case. All right, so that's t of n. That's time, right? So that should go all the way to, let me move this over here. Okay, so this is my t, okay? And you can scroll down here, you can see it goes all the way to 10 to the negative 6, okay? So t starts from 0, 100 data points from time equals 0 right here to time equals 10 to the negative 6. Okay, so that's my t. So that's column 0. So what's column A? What's column 1? I'm sorry. What's concentration of A? A of n. So the concentration of A for point n would be what? Which column? Column 1, right? So click on this and then type 1. That's telling me, I'm telling Mathcad that concentration of A is in column 1 of matrix Z. Okay, space bar, open bracket, that gives you the subscript, and that would be the nth element. Okay? And now over down here, I can say A of n equals, and this is the concentration of A versus time. Question, Joe?
I think I may have got it. Mine's not working.
Okay. Let me just finish this up. B of n would be what? Call it out for me. Would be the second column of Z, right? So I'm going to type capital Z. And from the toolbar, pick up matrix column, or you can type Control 6. That's a shortcut for it. I want the second column of matrix Z, because that's going to hold the values for the concentration of B. Space bar. And then how do you get the subscript n? Open bracket n. Okay? So that means B of n here is equal to, these are the concentrations of B. Note that B starts off at 0. You don't have B to begin with, and then as time advances, B increases. Okay? So let's plot those. Let me put them here. Oops. What did I just do? Let me zoom back out. Let me plot from n equals 0 to n point. So 0, starting point. The next point is point number 1. Semicolon would give you your dot dot, right? To get that dot dot, you type semicolon. So you start from 0, 1, all the way to end points. So you're plotting your end points. Okay, I'm going to insert a graph. XY plot. What do I want to plot? A versus time, right? So A of n versus T of n. And there is my exponential decay right there. Okay. This is what we get. And what happens if I were to plot B of n? So just click over here, space bar, comma, and then B of n versus time, and there's your reversible reaction right there. Okay, let's do a little bit of an exploration here. What do you think will happen if I were to, let's say, extend my Tmax to 5 times the original value? So I'm going to change my Tmax to 5 over K1F, and let's see what happens. Okay. And you'll notice what happened here. You've reached At 5 microseconds, what's happened? You've reached equilibrium, right? A and B have leveled off. Is this the correct equilibrium constant? What happens at equilibrium? K1F times A at equilibrium must be equal to what? The forward rate must be equal to the reverse rate, right? So K1R times B at equilibrium is your reverse rate. So that's V1F equals V1R at equilibrium. And what do we get? What should this ratio of B to A be equal to?
Yeah, define it either.
Oh, all I did was change the value of T max.
Not graphs, just like tell. Like all I did was
Okay.
your T-max also changed.
Yeah, the T max must change.
Oh, alright.
I changed the formula for T max. I just extended it 5 times further into the future.
There we go.
Okay. So now, if you know that K1 forward A equilibrium equals K1 reverse times B equilibrium, what is the ratio of B to A at equilibrium? B equilibrium over A equilibrium, products over reactants, would be K1 forward over K1 reverse. And so what should that number equal to? The number we picked was the same, right? For forward and reverse. So that's 1. You can see A and B approach an equal value at equilibrium. You got it? Okay. Now what would happen if I were to make my KF twice as large, K1 forward twice as large as my K1 reverse? What do you think is going to happen? Look at this equation right here. If I were to double this, what's going to happen to my B compared to my A? My B at equilibrium will be twice bigger than A, right? So this B is going to go up further, right? And this A is going to go down. And this ratio at equilibrium will be 2:1, right? B to A ratio. And let's see if that's in fact what we'll get. Okay? So I'm going to go ahead and scroll back up here. I'm going to change my K1F. I'm going to double it. So instead of 10 to the 6th, okay, I'm going to call it 2 times 10 to the 6th. So times, 2 times 10 to the 6th. Okay, I've changed my K1F, and let's see what happens now. Look at what happens. What's the B to A ratio now at equilibrium? At equilibrium, B equilibrium over A equilibrium is 2:1. K1F over K1R is going to be equal to 2. Okay? What's going to happen if I reverse it? I make A double K1F the same. I make K1R twice K1F. What's going to happen? So I'm going to make my K1F change it back to 10 to the 6, and I'm going to make my K1R 2 times 10 to the 6. Okay? And if I scroll back down here, get rid of this. Look what happened. What's your B to A ratio this time at equilibrium? This is going to be 1/2. That's K1F over K1R. This time we set that to be equal to 1/2. Okay? 10 to the 6 over 2 times 10 to the 6. Okay, so the nice thing about this is once you've got something set up, you can play around with your case. And so this is a good way for you to explore, for example, the steady state approximation. Remember, it works under certain conditions when this k is much larger than that k and all of those. You can do those types of explorations, and that's what I'm asking you to do in the exploration section for this lab. Okay. Now, what will happen if I were to make this irreversible? What would I have to do if I want this to be irreversible? I'm going to let the reverse rate constant equal to 0, right? So let's try that. And I'm going to make my reverse rate constant equal to 0. So right here, okay, I'm just going to change that to 0. Okay? And let's see what happens. What happens at equilibrium now? A completely disappears and it's completely converted to B. So this is the irreversible condition. Okay? Now, what did we say? How can we tell that we have an irreversible first order rate law? What would you have to plot? You plot ln of A versus time, right? So if let's say we were to plot ln of A of n versus time. I thought it did. Okay, ln of A of n versus t of n, you can see it's a straight line. What's the slope of this line? The slope of this one, you should expect this slope to be equal to negative k1f, right? And you can see, what's our k1f? We had our k1f here set to 1 times 10 to the negative 1 times 10 to the 6th. Okay. And you can see that if you have a change in the log by 1 unit, okay, from 0 to negative 1, okay, if you pick these 2 points right here, your slope would be negative 1 minus 0 over 10 to the negative 6 minus 0. See? The time it takes for the logarithm, the natural log, to drop by 1 unit is 1 over k. And that's called the lifetime, right? 1 over k1f is called the lifetime. That's the time it takes for the natural log to drop by 1 unit. That's the slope, 1 lifetime. Okay, so 1 over tau, negative 1 over tau is the slope. So you pick any 2 points on that graph, you get a slope equal to negative kf. All right. So that's what you're going to need to do. And I have explorations here for you to do. You'll be looking at parallel first order reactions, and then you look at reversible two competing reactions, so you can explore the concepts of thermodynamic and thermodynamically favored and kinetically favored products. Okay. So who's having trouble with? Okay. Let me go ahead and stop this